While the entire internet is busy talking about Booster 19 splashing down in the Gulf, there's one detail from Flight 12 that almost nobody is bringing up. Ship 39's heat shield just survived re-entry conditions tougher than what SpaceX actually designed it for. Not tougher by a few percent. Tougher because an unplanned engineering decision left the nose heavier than expected, before plasma even made contact, and it held. According to post-flight disclosures, not a single tile was burned through. Here's the question I want you to sit with. If this is one of Starship's most important wins, why aren't you hearing anyone talk about it? Let's break down why, including the two small Starlink satellites that nearly every analysis out there has overlooked. You won't look at Flight 12 the same way again. So what exactly made Ship 39's re-entry tougher than designed for? The answer lies in a detail almost every Flight 12 breakdown has glossed over. The header tank. The whole internet knows Ship 39 lost a Raptor vacuum engine roughly 3 minutes into the burn. Everyone's talking about how the second engine cutoff phase ran more than a minute long to compensate for the missing thrust. Because the trajectory drifted after losing that engine, SpaceX made the call to skip the planned in-space Raptor relight entirely. Drop a test, reduce risk, play it safe. But that decision carried a physical consequence. The header tank in the nose still had propellant on board when re-entry began. Picture it this way: you design a car for a crash test with an empty fuel tank. Every calculation about center of mass, about how forces distribute across the chassis, assumes that baseline. But on test day, the car has to run with a full tank up front. Center of mass shifts forward. Crash forces distribute differently. Every load-bearing point takes on stress the simulation never accounted for. That's exactly what happened to Ship 39. The nose was heavier than designed. Center of mass shifted forward. The angle of attack into the atmosphere changed slightly. Heat distribution across the vehicle deviated from what the sims had prepared for. The heat shield was operating in conditions it had never been specifically tested against. The heat shield held, and the heat shield experiments. And here's the part worth discussing. It held. According to post-flight reporting from sources tracking the program closely, not a single tile burned through. No signs of plasma penetration anywhere on the vehicle body throughout the primary re-entry phase. In aerospace engineering, there is a concept worth committing to memory: safety margin. When a system handles more than expected, that's a signal the design has matured. Not just adequate on paper, actually carrying enough buffer to absorb off-nominal scenarios. This isn't trending news. It isn't a viral moment. It's the kind of engineering evidence that thermal engineers look at and exhale because it tells them their tile design approach is pointing the right direction. This is the first time we've seen that clearly with Starship's heat shield. And one more detail worth flagging before moving on. On Flight 12, SpaceX didn't just fly a single standard tile spec. They mounted multiple experimental arrays on this same vehicle. Different adhesives, different attachment methods, possibly different tile formulations, all on one flight. The intent is straightforward: gather comparative data under identical re-entry conditions. Which array holds up better? Which one shows degradation? It's the kind of experiment you can't run on the ground with enough fidelity. You can't replicate 1,500 degrees Celsius plasma in a lab environment. You have to fly real hardware, take real heat, then see which array comes back intact. That's how you accelerate learning. Not one flight, one answer. One flight, multiple answers in parallel. The historical lesson from Space Shuttle and Columbia. To understand the scale of what just happened, step away from Starship for a moment and look back. The only reusable vehicle in history you can place alongside it is the Space Shuttle. After every flight, the shuttle required roughly 10 weeks of heat shield inspection. 10 weeks. For one flight. Every tile was hand-inspected for cracks, chips, bond damage, gaps. Dozens of technicians, magnifying lenses, flashlights, checklists running thousands of items long, all for a simple reason: The heat shield is what keeps the crew alive. In 2003, a piece of foam insulation broke off the shuttle Columbia's external tank during ascent. It struck the leading edge of the left wing. The damage wasn't large. If it had been spotted on orbit, a rescue plan might have been possible, but nobody saw it. 16 days later, when Columbia began re-entry, plasma cut through that breach. 7 astronauts died. I bring up Columbia not to be dramatic. I bring it up because after Columbia, NASA was forced to create a new procedure. They called it the rendezvous pitch maneuver. Every shuttle from that point on, before docking with the International Space Station, had to flip on orbit so the station crew could photograph the belly through the windows. That was the only way to verify the heat shield was intact before coming home. It took 22 years for that lesson to become standard procedure. And this is exactly where we need to pause. Because Flight 12 just did something that rendezvous pitch maneuver was only a primitive version of. 2 Starlinks and the self-scanning maneuver. Every Flight 12 analysis mentions the number 22. Ship 39 deployed 22 objects from the payload bay. That's nearly triple the previous flights, a significant jump in deployment rate and capacity. But here's the detail being skipped. Those 22 objects weren't identical. 20 of them were mass simulators. Metal slugs matching the form factor and mass of an actual Starlink, used to validate the new deployment system. That's the same class of payload flown on previous flights. Nothing new functionally, just a test of cadence and volume. The other 2 were real Starlink V3s, functional, antennas, small onboard thrusters, independent control systems, and most importantly, they carried imaging hardware. This was the first time SpaceX put Starlink 5-3 hardware in orbit, a test flight of a test vehicle, and they still made room for 2 operational satellites doing real work. That's how SpaceX uses every flight to pull data in parallel. No flight goes to waste. But the interesting part isn't the deployment. The interesting part is what happened next. After deployment, Ship 39 didn't just coast on a straight path. It executed a maneuver. It rotated so the 2 satellites could scan its entire heat shield surface. Read that line again. A spacecraft just deployed 2 of its own satellites, then flipped to let those satellites image its own heat shield before re-entry. This is the automated version of the rendezvous pitch maneuver. But to see why I call it automated, look at what the shuttle required to do the same thing. The shuttle needed the ISS. It needed the station crew at a window with a camera. It needed sunlight at the right angle. It needed the standoff distance between shuttle and station within a narrow envelope. It needed the shuttle to be on an ISS approach trajectory in the first place, meaning not every mission could even attempt this. And the whole procedure was only designed after Columbia was already lost, 22 years before it became standard. Starship? Deploy satellites from the vehicle itself, on any orbit, at any point. No crew required, no station required. 2 dedicated satellites for this exact task, riding on the very vehicle they're inspecting. My honest read is this. NASA took 22 years after Columbia to get to the rendezvous pitch maneuver. And that procedure still depended on the shuttle meeting the station. SpaceX, on Flight 12, demonstrated a version that goes further. A version that doesn't need to meet anyone, doesn't need to wait on anyone, doesn't need specific lighting conditions, and most viewers didn't even register that it happened on this last flight. This is the kind of technical progress that gets buried because it doesn't have a viral moment. No tower catch shot, no live stream explosion to cut into a TikTok clip. Just a vehicle quietly flipping in space, 2 small satellites taking pictures, and a data stream flowing back to mission control in Hawthorne. If you're finding this kind of analysis useful, the kind that digs into the details other channels skip past, hitting like and subscribing genuinely helps this type of breakdown reach more people. Now back to the part that matters most. Why this detail shapes the future. The link to Artemis, HLS, and future crewed missions. Here's the part worth thinking through carefully. Consider this scenario. In 2028, a Starship carrying NASA astronauts for an Artemis mission is heading back to Earth after a lunar resupply. The heat shield has a single cracked tile from a micrometeoroid strike in lunar orbit. Nobody knows. Re-entry begins at 27,000 kilometers per hour. Plasma cuts through that crack the same way it cut through Columbia's wing leading edge. This is exactly the failure mode that self-scanning addresses. If a satellite deployed from the vehicle itself can detect heat shield damage before re-entry, the vehicle can skip the landing attempt and stay on orbit awaiting rescue. The crew survives. That's not a nice-to-have capability. It's a hard requirement for any crewed Starship to be cleared to fly. NASA will never sign off on a crewed vehicle without a way to verify heat shield integrity pre-re-entry. Post-Columbia, that's a red line that doesn't move. And Flight 12 just demonstrated the first iteration of that capability. I need to be precise here to maintain credibility. We haven't seen actual imagery from the two satellites. SpaceX hasn't released it. We don't know the scan resolution, whether it can detect microcracks in tiles, whether it works in every lighting condition. This is a new capability with preliminary proof of concept, but resolution and reliability need additional data before NASA clears it for crew. That said, going from zero to a first version is a much bigger leap than going from the first version to a refined one. And Flight 12 just cleared the bigger gap. Why nobody is talking, plus 3 questions for Flight 13. So back to the question in the title. Why is almost nobody talking about this? Straight answer. Because it isn't dramatic. A booster catch is a spectacle. A 145-meter tower catching a 70-meter rocket. You can clip 10 seconds of it, post to X, and it goes viral on its own. A heat shield doing its job is an invisible win. You have to read telemetry. You have to understand thermal dynamics. You have to know what the rendezvous pitch maneuver is to grasp what those two satellites mean. Media and social platforms reward visual shock. They don't reward safety margin. That's the problem with measuring progress on a program as complex as Starship. It's easy to track the wrong metrics. You count whether the booster caught. You count whether something exploded on the live stream. You forget that real progress on a reusable program lives in numbers that don't trend. Heat shield margin, on-orbit self-diagnosis capability, thermal data accumulated flight by flight. I want to be fair about this. Catching a booster is a mechanical problem. SpaceX has solved it 3 times with version 2. It can probably be solved again quickly with adjustments. It's the kind of issue that gets fixed between flights. A reusable heat shield is a materials problem. It takes many flight tests to gather enough data. You can't fix it with software. You can't solve it once and be done. Every flight without burn through, like Flight 12, adds another data point to the reliability curve. That curve is what determines when NASA is willing to put astronauts on this vehicle. That curve is what determines when SpaceX can say, we're ready for Mars. So for Flight 13, on the heat shield specifically, there are 3 concrete questions worth watching. Question 1. How did Flight 12's experimental tile arrays perform? SpaceX tested multiple adhesives and attachment methods on a single flight. If Flight 13 scales up one of those arrays into the standard windward design, that's a signal they've found a better formula. If Flight 13 keeps experimenting with multiple arrays, the search isn't over yet. Question 2. Will SpaceX release imagery from Flight 12's 2 Starlink 5-3 satellites? If they do, the scanning capability has matured enough to share, and possibly ready to demonstrate to NASA. If they don't, either the resolution isn't where they want it, or there's a technical issue they're quietly working through. Question 3. Will they repeat the deployment of 2 functional Starlink V3s on Flight 13? If yes, orbital heat shield scanning is on track to become standard procedure for every Starship. If no, it may have been a one-off experiment and they're heading a different direction. These 3 questions aren't specific predictions. They're a lens for watching Flight 13. So you know what to look for when the live stream starts, instead of just waiting for the booster catch. The data suggests that if Flight 13 continues to demonstrate heat shield integrity across varied re-entry conditions, SpaceX could begin testing ship catch attempts late 2026. That's the optimistic scenario. If the opposite, if Flight 12 data analysis surfaces tile damage invisible to the naked eye, or if the two scanning satellites return something SpaceX would prefer not to release, the entire Artemis schedule could face unscheduled slippage. Both scenarios are on the table. That's why Flight 13 matters more than most people are giving it credit for. And there's one more piece of Flight 12 information SpaceX still hasn't fully disclosed. Something tied directly to those two satellites. Something that could reshape how we read Starship's entire reusability strategy over the next 24 months. Thanks for breaking this down with the Space Brief all the way through. If the video added value, hit like, share, comment, and subscribe. Tap the video alongside to keep the story going with me.